Now that we know how to do approximation methods, we're going to move beyond the problems that we can solve exactly. So in chemistry, right, we want to look at things that have more than one electron, something like helium or carbon or any of the other elements on the periodic table. And so in chapter 8, we're going to start our journey into the actual applying this to more chemically relevant systems. So to start with in chapter 8, we're looking at multi-electron atoms. So this is anything like helium, right, where we have 2 protons, 2 neutrons, and 2 electrons surrounding our nucleus. And going beyond this, of course. But we're going to start with helium as sort of our first, simplest example of a multi-electron atom, and then we'll talk about more general concepts as we continue through this chapter. And so what we want to do is we want to write the Hamiltonian and the Schrodinger equation for helium, and then figure out how are we going to solve this? What are the methods that we can use to do this? And these are going to be based on variational theory and perturbation theory, like we talked about in the last chapter. So let's go ahead and write out the Hamiltonian for helium. All right, so we'll do the same things we did for hydrogen. Assume the nucleus is fixed, so we don't have to worry about its kinetic energy. And we'll just worry about the kinetic energy of the electrons. So we'll have a kinetic energy term, so we'll label this number 1 and number 2. We'll have a negative h bar squared over 2 mass of the electron. And then we'll have a second derivative with coordinates corresponding to electron 1. Then we'll have another term that looks exactly the same, but is for electron 2. And then, so these are kinetic energy here. And then we need to add the potential energy. All right, so we'll have the potential energy of the electrons being attracted to the nucleus, as well as the electrons repelling each other. Okay, so we'll have the attractive forces, so that'll be these terms here, 2e squared over 4 pi epsilon naught r1. We end up with 2 here because we have 2 protons in our nucleus. And then we have a similar term for electron 2. Only difference being, we use R1 versus R2. All right, so these are our attractive Coulomb forces, Coulomb potential energy, I should say. And the big difference we have compared to hydrogen is that now we also have a repulsive term because we have more than one electron present. So we'll have a positive term because it's a repulsive term. It increases the energy of the system. And that'll be e squared over 4 pi epsilon naught r12. So r12 is the distance between electron 1 and 2. Whereas R1 and R2 are the distances from each electron to the nucleus. All right, and we're beginning to see why we have problems solving this. The big problem with solving this multi-electron atom system, getting exact solutions, is this term, right? This electron-electron repulsion. We can't disentangle the electrons from each other. Our usual technique of separating variables and getting exact solutions isn't going to work for helium. And so that's the big takeaway here. One other thing we can do is, we have a lot of terms that show up over and over again. For example, we, have lots of H bars that show up. The mass of electrons constantly showing up. We have this 4 pi epsilon naught. And so to simplify things, theoretical chemists use a set of not equations, but a set of units that we call atomic units. And this lets us write things in simpler units, and then we use different unit conversions. So for example, the atomic unit for mass is the mass of the electron. The atomic unit for charge is the charge on an electron. The atomic unit for angular momentum is equal to h bar. And the atomic unit for distance is the Bohr radius, which, just as a reminder, is 4 pi epsilon naught h bar squared over, there's no 2 there, over mass of the electron times the charge of the electron squared. And the atomic unit for energy is known as a Hartree, and often given the symbol EH. And this is equal to ME, mass of the electron times charge of the electron to the fourth over 16 pi squared epsilon naught squared h bar squared. And this is based roughly on the energies of the hydrogen atom. And then the atomic unit of permittivity, this is this epsilon naught that keeps showing up, is 4 pi epsilon naught. So in essence, what we do is we set all these units equal to 1 in atomic units, and our Hamiltonian for the helium atom becomes a lot simpler. So basically set these equal to 1 unit, essentially, and the Hamiltonian becomes minus 1/2 del 1 squared minus 1/2 del 2 squared minus 2 over R1 minus 2 over R2 plus 1 over R12. And specifically, this is in atomic units. And so it becomes a lot simpler just to write this out. We just remember that if we want to convert between different unit systems, we have the definitions above that we use.